Hello everyone. Today we're going to learn 2.3, how to analyze graphs of functions. So first, a couple things you want to take notes on, things we're going to look for in graphs. First are certain ordered pairs. So the first number is the x-coordinate, second number is the y-coordinate. Y is the same as f of x, so it's just more, now with this functions unit we're going to use f of x more because it's just, it's more efficient. The domain is all the x values the graph covers. So when you're looking at a graph, just look at all the x values that the graph spans, and all the y values that it spans is the range. To check if a graph is a function, you use the vertical line test. So you draw a vertical line, and if at any point you could draw a vertical line on the graph and it hits it at 2 points, it's not a function. If that line does not exist, then it's a function. Zeros are important. They're also known as x-intercepts. They're any point on the x-axis, any point where y is equal to 0. So that's why they get that name. Intervals where f of x is increasing is any interval, so from x1 to x2, so x2 is bigger, more to the right, f of x1 is less than f of x2. So at any interval where the y values get bigger as you look from left to right, it's increasing. If they get smaller, if it's going downhill when you look at it from left to right, it's decreasing. And if the y values stay the same, then it's constant. So let's, well, actually a couple more things. Relative minimum and maximum, they're just peaks and valleys. So any point in the function where you have like a little dip and then it goes back up, this point right here, this point right there would be a relative minimum. And if you have a peak like that, or in this little graph here, you got two relative maximums. So at any interval, if there's a value for, let's say a, f of a is less than all of f of x, so like on this interval, this would be a comma f of a. If that's the lowest point on the interval, so the interval would be like all these x values that we can see in that part of the graph, that's a relative minimum, so we represent it as a point. And if it's a peak rather than a valley, then it's called the relative maximum. Alright, so let's practice this. So first, f of -2. That's asking for the y value when x is -2. So you're pretty much looking, at where this line, x equals -2, crosses the graph. And it's right here. So f of -2 would be +2. Alright, and f of 2, well, that is the y value where x is 2. So see how there's an open circle right there? That means that, but there's a closed circle right here. So if I drew the line x equals 2, it would cross the graph at this point, 2 comma 2. So f of 2 is also 2. So right there we know this function is not one-to-one because there's a repeated y value. X, if f of x equals 2, so now we're looking at when does this graph, sorry, I'm having trouble drawing stuff. So when is the y value on this graph equal to 2? So if I draw a red line now, that happens at 2 points. It could be at x equals 2 and x equals -2. So that's, number 3 is like questions 1 and 2, but instead of asking for y values given x value, it's asking for an x value given a y value. The domain is all the x value that the graph hits. So this arrow over here is showing that it goes on to the left forever. And then if we follow the graph, it hits all these x values. And then you get to 2, and there's a closed circle right here, and an open circle here, which means there is a discontinuity, but so at 2, it jumps from y equals 2, and then for any value of x greater than 2, the graph is now y equal to 3. And the arrow goes all the way to the right, which means it's going to span all these x values. So in this case, the domain is going to be x belongs to the set of all real numbers, because it kind of hits every x value. As for the y values, let me erase what we got here real quick. So as for the range, well, it looks like the lowest point is right here at y equals 0, but it does go up forever, even though there's a jump over here and it's not hitting these y values greater than 3 on the right part of the graph, the left part of the graph does go up and to the left forever. So the range would be y is greater than or equal to 0, because it looks like it'll span every y value that's positive or 0. Alright, as for the zeros, we're looking at when does the graph cross the x-axis. So that just happens right here at 0, 0, or x equals 0. Either way, representing it's okay if I ask for a 0. Is it a function? Well, the only issue where we might have using the vertical line test is right here. But notice that open circle, you could think of the vertical line going through the circle and then hitting the graph of f at only one point right there. It does not hit the graph at 2, 3 because again there's an open circle. And if you draw a graph just to the or a line just to the right of that point, it's only going to hit f at one point, and that'd be at 2.1, 3. So this graph is a function. We'll say yes because it passes the vertical line test. Alright, intervals of increasing. Well, pretty much any x intervals where the graph is going up. So if you look at the graph from left to right, from negative infinity to 0, the graph is decreasing, it's going down, and then it starts increasing starting at 0. So on the interval from 0 to 2, the graph is increasing. And as we said before, the graph was going down from negative infinity to 0, so the intervals of decreasing would be all x values from negative infinity to 0. And then it's constant, I don't have that there, but f is constant when x is greater than 2. F it could be called constant because it's always equal to the same y value, which in this case is 3. Relative minimums, well, that's going to be an ordered pair. Remember, the two we just did were intervals, like x values. But when we do relative minimums and maximums, those are points. So the relative minimum is going to be right here at the origin, that little valley that we hit at 0, 0. Relative maximums, there is no relative maximums. It goes up forever if we look at it from the middle of the graph to the left, but that's not a maximum because it keeps going up. It never really reaches a max. And in order for it to be a maximum, there's got to be a peak. It can't just be constant. There has to be y values that are less on either side of the maximum. So there is no relative maximums. Alright, and then last two things, is it even or odd? It looks even, but at certain points, like if you just use this part of the graph, it would be even because it's got that y-axis symmetry, but it's not. Once you go outside of this little box I made, there's no more even symmetry or y-axis symmetry. So the function is not even, and it's not odd because you could disprove it with one point. If there is a point 2, 2 on here, like there is, then there should be a point -2, -2, but there isn't, so it's not odd. And then is it 1 to 1? Well, we would use the horizontal line test for that, and it would fail miserably. Not miserably, but at a bunch of, you could draw a bunch of horizontal lines that hits the graph at 2 points, so it is not 1 to 1. Not 1 to 1. Cool. Alright, let's analyze another graph. So again, f of 1 is asking what's the y value when x is 1. So we have some discontinuity going on here. If we look at when x equals 1, there's an open circle and a closed circle. So that means we're going to go with the closed circle. So y is, if you plugged in 1 into this function, you would get -1. And if you plugged in 4, though, there is a vertical asymptote. So this dotted line here shows that the graph gets really, really close to it on both sides, really close to 4, but never touches it. It approaches infinity on both sides, but the graph will never cross over a vertical asymptote. It can cross over a horizontal asymptote, but vertical asymptotes will occur if you have an equation that certain domain restrictions. Like for example, if we graphed 1 over x, y is equal to that, there would be a vertical asymptote at the y-axis. So in other words, if you plugged in 0, and that's where the vertical asymptote occurred at x equals 0, you would get undefined. So in this case, if we do f of 4, we get undefined because the graph never crosses x equals 4. Alright, what's x if f of x equal to -2? So we're going to look at, alright, when does the graph hit -2? And it looks like it's only happening at one point right here at 2, 2. So the x value would be x equals 2. When we look at domain, if we start from the left, there's an arrow there which shows that, alright, the graph's going to hit all these x values. And then if we work our way over, it hits all these x values all the way to 1, where there's a jump discontinuity. So the graph isn't continuous. It jumps from one y value to another, but it's still going to hit x equals 1, and all of these x values up until 4. And then right here we have a discontinuity. The graph is never going to hit 4 on the x-axis, but it is going to hit the rest of these x values because of the arrow right here. So the only domain restriction we have is x cannot equal 4. So that's going to be our domain. X cannot equal 4. As for the range, so let's erase this. Now, if we just look at this part of the graph, starting at 2 and going up, we see that, alright, the range is at least y is greater than or equal to 2. Alright, and right here, it looks like the graph is flattening out, and right here it's kind of tough to tell whether the graph is going down or flattening out. So there's really not enough information to know for sure, but here's what I'll tell you. If I ever want you to know that there's a horizontal asymptote like this, then when you look at the graph's end behavior, if you go towards infinity or negative infinity, if this dotted line was here, then I could say, assume that this graph flattens out and never crosses the x-axis. Alright, or if I didn't want it to flatten out, if I want you to think that as the graph is going to continue to decrease, then I would make it obvious. So in this case, it's kind of hard to tell, and so I just wanted to point that out. If you're not sure what the end behavior of the graph is, you could just ask, or it should be indicated by an asymptote, and it's not in this picture. So let's just assume that there is a horizontal asymptote at x equals or y equals 0. Then in that case we could say the range is y is greater than or equal to -2. Alright, the zeros, well, it crosses the x-axis at that point, so 1, 0 would be x equals 3. And you might be wondering, well, you just said there's a horizontal asymptote there. Well, graphs can cross horizontal asymptotes. Horizontal asymptotes just show you what's happening at either end of the graph. They just show end behavior. So if the graph is getting close to the vertical asymptote at either end of the picture, then you assume it doesn't cross and gets really close to it. But in the middle, like in the meat of the picture, it can cross the horizontal asymptote, and you'll be able to tell. Alright, is it a function? Well, it passes the vertical line test. No matter where we draw a vertical line, it's going to hit the graph at one point. Even right here, it goes through the open circle and then hits the closed circle. So all these vertical lines hit the graph at one point. So yes, it is a function. Intervals of increasing. Alright, so look at the graph from left to right. When is it going up? From here to here, it's going up. So from negative infinity to -2. And then union, so now here it's going down. Alright, and then here it's going down. But from x equals 2 all the way to x equals 4, the graph is increasing. And then everything after that, if you look at it from left to right, it's going down. So that right there would be the interval of increasing. Interval of decreasing, so same idea, but look at when is the graph going down. So from -2 to 1, the graph is decreasing. And then from 1 to 2, it's decreasing. So we'll say from -2 to 2, the graph is decreasing. Alright, union, it's going up from 2 to 4, and then from x equals 4 to infinity, the graph is going down. It's decreasing. It has negative slopes at all these points. So we'll say from 4 to infinity, the graph is decreasing. Relative minimum, so now we're looking for points. So there are little valleys in the graph. So I see one just right here at 2, 2. That would be a relative, well, 2, -2. That'd be relative minimum. There has to be y values on either side directly next to it that are bigger than at that point. That's the relative minimum. Here would be a relative maximum at -2, 3, because on either side of that point, those points have y values less than 3. Is this function even or odd? No, there's no symmetry, so no. And this function is not one-to-one because it fails the horizontal line test at a bunch of points, or a bunch of lines. There's one example of them. Alright, let's learn a new function, and it's called the greatest integer function. And what it does, it's got these weird brackets around the number, and whatever the number is, it pretty much rounds it down. It's equal to the greatest integer less than or equal to x. So like an absolute value to a positive number, where it does nothing, absolute value of 2 is 2, absolute value of 7 is 7. If you have the greatest integer function of an integer, then that does nothing. So like the greatest integer function value, or greatest integer function of -1 is going to equal -1, and the greatest integer function of 1 will equal 1. But something like 0.5, you're going to take the biggest integer less than or equal to 1/2. So the next integer below 1/2 would be 0. With -1/2, it would be -1, because if you were to round up to 0, now you're going up. You could think of this as just the rounding down function. Greatest integer function of 0 is 0. 0 is an integer. The greatest integer function of 1.5 would be 1. So graphs of these will look like little steps almost. So if I ask you to graph y equals the greatest integer function of x, first you should plot points on it. There's plot points of this function, just y equals x. So first ignore the greatest integer part and graph that, but don't connect the dots. So you'd have whole number points like x is equal to 0, y is equal to 0, 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, and so on and so forth. Alright, because these are the x values that are integers, and if you plug an integer into the greatest integer function, nothing's going to happen because it's going to round down to the same number. Alright, but what if you plugged in something like 1/2? So that would happen right here on the x-axis, 1/2, but it would round down to 0, and that would happen for any x value less than 1. So you have an open circle, because if you plug in 1 for x, you get 1 for y. And if you plugged in any number greater than 1 but less than 2, the greatest integer function of that number would round down to 1. Same thing would happen on this interval and that interval. So you get these little steps. Alright, and you don't have to graph every single one you could fit on the graph, but you get the idea. Alright, and it's kind of hard to draw in here, but the graph would look like a bunch of these where you have a closed circle, and then for that whole x value up until it hits the next integer, it would be an open circle. That's what these would look like. Alright, so we can kind of use that strategy to graph a more complex linear greatest integer function. So y is equal to 2 times the greatest integer function of x plus 1 minus 3. So if I were to just ignore these little brackets and think of them as parentheses, I would get this function in slope-intercept form. Y equals 2x minus 1. So I'm going to just plot points as long as the x values are integers, because if I plug those x values into here, then if you add 1 to it, it would still be an integer, and then these brackets wouldn't do anything, thus yielding this equation right here. So I'm going to plot points on this graph. So I'm going to start at the y-intercept of -1 and then use a slope of 2 over 1. So we go up 2 over 1, up 2 over 1, up 2 over 1. Alright, now again, this only works if you plot points that have x values that are integers. So notice how this point has an x value of 1, 2, 3, 4. Okay, if I had any point that landed in between these tick marks on the x-axis, then you wouldn't graph them. So now we're just going to connect the dots with, or complete the picture with these little steps. Because if you think about any point, any x value that you plugged in on that interval would give you a non-integer inside this part of the function, so let's say you plugged in like 1/2, you'd get 1 plus 1/2, which then when you applied these greatest integer function things over here, it would round down and you just get 0. And then times 2 would give you 0, and then minus 3 would still land you right here on the graph at y is equal to -1. Alright, so I believe that's it. Yep, that's 2.3. Hope you enjoyed it, and I'll see you in class.